Okay, thank you. Yeah, so very excited to be here to talk about our paper on membership inference attacks from first principles. This is joint work with my colleagues now, all of whom are at Google. So a membership inference attack asks a very simple question, which is, was some particular machine learning model trained on a given example? Recall that the way that machine learning models are trained is you have some training data set, and then from here you use some algorithm like stochastic gradient descent to get some machine learning model out of this. And all that we ask for membership inference is, we have this image maybe of a cat. Was this image any of these images contained in the training data set? It's a very simple question. And there's a lot of reasons why you might want to be able to answer this question. They range from everything from just curiosity. Maybe I want to know what some company trained their model on. Did they use my data? To questions of reconnaissance. Maybe I want to, if I know what data they trained on, maybe I can attack them better with some future attack. To motivations like data extraction. It turns out that membership inference attacks are the building block that we use to actually extract data from trained models. And so better membership inference attacks allow us to do the data extraction better. Or finally, even I might want to audit the correctness of some privacy algorithm, and I might use the attack in order to ensure that the algorithm is actually as private as it's claimed to be. So in this talk, I'm going to present to you a first principles approach to designing membership inference attacks, where we try and reconsider this problem and just say, what do we think is the right way of performing these kinds of attacks, and hopefully develop something that's both simpler and also more powerful. Okay, so the basic membership inference setup goes like this. You want to predict the probability that you believe that some example was in the training data set for some machine learning model, and we'll call it quantity A, and then quantity B is the inverse, the probability you think it's not in the data set. And then, trivially, if quantity A is greater than quantity B, you think that you say, yes, it's a member, otherwise you say non-member. The interesting question then is, how do you compute these quantities here? And for this, let me just zoom in on one of these because the other one is symmetric, and ask how we calculate this probability that something is actually in the training data set. What we're going to do here is essentially we're just going to treat this, like any modeling problem, and we'll try and first frame it like this way. We'll say, what is the probability of observing these particular neural network weights under this distribution of all possible models that we could have seen, given that it was trained on this image? This clearly is the right thing to do, sort of by definition. This is what this equation actually means. The problem is that you can't actually compute this. Like, neural networks are millions or billions of dimensional objects. You can't just ask, what is the probability of this billion-dimensional object through some simple statistics. So there's this challenge here, right? Like, you can't enumerate this distribution space. And so directly asking this question is not going to work. So we'll have to just do something slightly different. So what are we going to do? Well, instead, I'll give you sort of one piece of background, which is something that's called a loss function. A loss function allows me to answer the question, how wrong was some model on an input? It's going to return for me a single scalar floating point value, which is a measure of how badly the model performs on this input. And so what we can do is we can take this correct formulation, which is what we would like to be able to compute, but we can't, and instead measure it somewhat slightly differently, and instead measure in the probability of observing this loss value for the model on this image under the distribution over all losses that we might see when training models on this image. And the reason this is easier to calculate is because now we're only asking for the probability of observing a single floating point value. This is something that's easy to calculate, and so it's much sort of more feasible. And I say it's easy to calculate, but I still need to tell you how we do it, and that's what I'm going to walk through next, is how we actually calculate these probabilities. Okay, so what I'm going to do is I'm going to take inspiration from this recent paper that performs the following experiment. Let's take the training data set, and we're going to randomly mask out half of the training examples. And I'm going to use this to train a machine learning model. I'll take this model, and I'll save it over to the side, and remember what data it was trained on. Then I'll take the same training data set, and I'll randomly mask out a different 50% of the data. And then I'll save this model over to the side and do this again. Take the training data set, mask out half of the training examples, train a model, and now I'm going to have a huge number of models. Now I take all of these models that I've trained, and I partition them into two sets. on the left, I have the models that saw a particular image during training, and on the right, I have the models that didn't see this image during training. Okay. Now what I can do from here is I can zoom in on the one on the left and say, okay, for each of these models, what was their loss on the image that I'm interested in? I can replace this with the scalar valued loss, and this gives me a distribution over losses. I can then go and I can ask exactly the same question for the other set of models that didn't see some image. I take these models, I get the single scalar value loss, and I get a new distribution. And now what I can do is I can compare these distributions. I can plot them on the same scale, and you can see that they're very, very separate. Like the distribution of losses that you happen to see when an image is in the training data set is very different from the distribution of losses when some image is not in the training data set, which intuitively allows us to say that it should be easy to attack this image because we can check, is it more similar to the blue distribution or the orange distribution, and then directly, fairly easily read off whether or not we think this is a member. And this works sort of by eye test, but we'd like to be able to have something we can actually measure in practice. So what are we going to do here? Like, we're going to need some way of actually measuring these distributions. Okay. So in general, whenever you have to measure distributions, there's two things you can do. You can come up with a non-parametric approach, which just gathers lots of data and then just directly look at the data. The problem with non-parametric approaches is they require training lots and lots of models. Now, to make these figures in this talk, I've done that. I've trained 10,000 models. But in general, this is not something you can reasonably ask people to do, especially for big models. So we're not going to take this approach because it's going to require training just far too many models. Instead, what we're going to do is we're going to take a parametric approach, which is this going to allow us to train many, many fewer models, but still estimate the distributions fairly closely. In particular, we'll need something like 32 models trained. Okay. So what this is going to actually let us do is estimate the distributions, but I need some way to actually estimate these distributions correctly. You can't just throw a Gaussian on top of anything. And so you need to have some kind of care that you're actually going to model this with some correct parametric distribution. This requires a lot of care for this talk. I've already done all that for you, and these things actually fit Gaussians very nicely. Maybe a big part of our paper is actually how to make these things fit Gaussians, and for details I encourage you to take a look at the paper for that. But if you do it all correctly, then you end up with two very nice Gaussians. And what you can do is you can look like where these two lines cross for the Gaussians, and this gives you a threshold where if the loss is to the left on this blue region, then we say that's a member, and if it's to the right of this threshold, we say it's a non-member. Okay, so this is what happens for one particular image of this cat. But what would it look like for a different image? Well, all you do is you repeat this process where you repartition the models under the new distributions for the new image you care about and recompute these statistics. And you'll get a new loss distribution. You can recompute this again. So for example, for this cat image, the decision threshold is somewhere around a loss value of 7. But here, we have these airplane images where I've just recomputed the statistics. And I can, relook at these Gaussians and see that the decision threshold here this time is somewhere around 1. So there's this very important observation from the paper, which is different images have very different histograms. And so it's easy to distinguish between both this airplane and for the previous cat, but they had different decision thresholds. And so any attack needs to be allowed to have these different decision thresholds. And this is a big thing that many prior attacks didn't allow. Okay, so again, you can model this as a Gaussian too. And one final thing that we can do that's nice with our technique is let me just zoom into this region of interest down in the middle. We can not only get a threshold, which is where these two values cross, but if I take any arbitrary point, I can look at the ratio of the blue line to the ratio of the orange and be able to tell you the probability that I think I'm right in my answer. And this is really, really powerful because not only can I be correct most of the time, but when I'm wrong, I'll have low confidence in my answers. So I'll know that I'm wrong, and it's going to make the results actually much stronger. Okay, so yeah, with that, let's actually start talking about some results. Which is how well we do. And as you might expect, given that we have the paper here, our results are sort of as good as or better than most prior work. This result is sort of just the average accuracy, and you see our numbers are bigger or something. But the problem is that this is an average case number. This is what people have been using in the past. This is an attack success rate on average over an entire training data set. I don't think that this is a very good number. Average case numbers don't work very well with privacy. For example, if I could say, I know for all of you in the audience, one digit of each of your credit card numbers, this would not be very informative. I know 6% of your credit card numbers on average, but one digit of each of your numbers is much less important than I know the credit card number exactly of all of you in the leftmost column. Like that would be a much more powerful attack, but the average, they're still the same, like they report the same quantity. So what we want to do is we want to have a metric which allows us to distinguish between these two facts. You can have attacks that are good on average, but not good at identifying any one particular person as being vulnerable. So for doing this, let me sort of zoom in on this one attack on the top, which has the second highest average accuracy and works quite well on average. And what I'm going to do is I'm going to show you for this attack what the ROC curve looks like. What the ROC curve shows, it's a true positive versus false positive evaluation of this attack. So you can think for any given point on this line, this corresponds to a given true positive rate and a given false positive rate. So this attack at this point, has some high true positive rate, but the false positive rate is quite high. Note that the way that ROC curves work, it's trivial to be anywhere on the upper right. Just make your attack always return yes. You'll have a 100% true positive rate. Of course, you make all the errors on false positives. And similarly, it's trivial to be on the bottom left. Just never say anything as a member, and you'll have 0% false positive rate. Of course, you have 0% true positive rate. So what you want is something to the upper left region. And the thing that we notice here is that for this attack, actually, at the low false positive rate regime, the area where you're actually able to say something specific about a few individuals, this attack performs about as well as random chance. It doesn't actually do a powerful attack at this low false positive rate, and this is the regime that lets us say something particular about individual users. Okay, despite the fact that, remember, on average, this attack worked very, very well. To make this very explicit, what I'm going to do is I'm going to take this plot, and I'm going to, instead of showing you this in this normal scale, I'm going to show you this in a log-log scale. Now, this is just fairly standard in security and malware evaluations, these kinds of things. We like to report log-log scales just to zoom in on the lower left region. And so I'm showing the same data, but you can see that at false positive rates less than 10%, the attack is roughly random guessing. Okay. And it's not true for this one attack. I'm not sort of singling that one attack out. For all of the attacks that perform well on average, they have very, very poor success rates at low false positive rates. Okay, so what about the other attacks? There are others of them in this table. So that's for these ones. There are some other attacks here. Notice these ones perform less well. So you'll take the first couple, they all tightly clustered on 59% attack success rates. These ones are 56%, 53%, so they're less good on average. But when you look at these attacks that were previously published, you find that they have a much higher success rate at low false positive rate. So this is one of the observations from our paper, is that there are lots of attacks that already exist in the literature which can succeed at this metric. They just haven't been evaluated this way before. And these attacks, we argue, are better, despite the fact that on average they do a little less well. Okay, and so maybe the surprising contribution from our paper is that not only do we have numbers that are more accurate on average, so that we beat the best average case numbers, we also beat the best true positive rate at low false positive rate numbers. So the attack that we have is sort of better, no matter the metric that you care about, it's doing the right thing, and because it's doing the right thing, it's easier to more correctly model everything. Okay. So this is the main set of results I'm going to present to you for this talk. Of course, in the paper, we have all kinds of other analysis that talks about what happens on different data sets, what happens, we do an ablation study across why what we have is better than what prior work, what pieces are most contribute to the attack success rate. We try and understand why some examples are more non-private than other examples, what's going to make this happen. I'd encourage you to look for all of these details and more for the paper for details. So with that, let me give sort of, maybe now a brief conclusion. This was not my conclusion. Welcome to IEEE S&P. Okay, if we can get it back. Should I just keep going? Okay, I'll keep going. I have only one slide. That's my favorite slide. Oh, okay, here we go. Okay, here's my conclusion. Basically, the conclusion may be somewhat controversial. Everything we know about membership inference attack results might be wrong. Okay, so let me say what I mean by this, because I mean something in particular. People have written lots of papers before that say things like, weight decay does not help with membership inference attacks. It's not a good defense. This result is true insofar as weight decay does not help on average, defend against membership inference attacks that work by using a single global threshold. That is a true result. Whether or not that result is interesting is a separate question. Like, I argue that what we should be asking is weight decay a valid defense at low false positive rates for the best attacks that we have? And that's something that now we no longer know the answer to. Basically, all of the results in the literature look exclusively at this average case number, for the most part, and use attacks that are quite poor. And so for the most part, we're going to have to reconsider many of these things that we think we know are true in order to see if they still remain true at low false positive rates with stronger attacks. Whether or not they do, I think, maybe it's slightly more biased so that the results transfer, but we don't know. And it's not just defenses. There have been things like, I've written a paper on how to do membership inference attacks with only being able to have hard label query access to a model. But we evaluated this only on average case numbers. Does it work at low false positive rates? I don't know. Maybe it does, maybe it doesn't. Someone's going to need to actually go and reinvestigate this. And notice, please, there is a huge asterisk here. I don't want to dismiss, all of prior work as being wrong. I just think we're going to have to be very careful about trusting which numbers we have from prior work in order to make sure that we can actually trust what we're doing here. So with that, thank you very much, and happy to take any questions.
Thanks, Nicola.
Yeah.
Very interesting talk. But my question is that, do you require to know the training data set except the sample that you're looking for?
Yeah, okay, so let me sort of make sure I understand the question right. Do I need to be able to train on the example that I want to evaluate on? For the full attack as I presented in the talk, yes, we need to train a model on this image. This is what we call an online attack, where we assume we can sort of get the point and then train a bunch of models and then give an answer. We also, in the paper, have an offline attack that sort of removes this assumption. It performs almost as well. I didn't give the figure here, but we have some figures in the paper that show how well the attack works in the offline setting. You lose a couple percentage points of accuracy, but it's almost as good.
All right, first off, awesome talk. I feel like every privacy paper should now include disclaimers for that stuff. My question is, assuming I would now use your approach for, let's say, dogs instead of cats, what are some of the pitfalls I should look out for?
What are some of the pitfalls for using
the approach in general? Yeah.
I see. Okay, so why would you not use this? Okay, great. There's a bunch of reasons. The first of which is it requires training several models. The nice thing about the simple attacks is you train one model, you compute one global threshold, and you're done. In order for this attack to work, we need to train at least 8 models. In some settings, training 8 models is easy. In other settings, in machine learning space, where people have training models with 500 billion parameters and it costs $10 million, telling them, please do this 7 more times so I can tell the privacy of this method, they'll say no. So we need, this is the main thing, is we need sort of a more computation cost. There are other factors that might contribute in the future. Because this is a slightly more involved setup, there are more places where things might go wrong. It's very easy to look at the loss for a global threshold and say less than or greater than some value. And so if people use this for evaluating its defenses, it's possible that it'll be easier to accidentally fool yourself in getting something wrong when using this as a defense evaluation tool. We've seen this a lot in adversarial examples where more sophisticated attacks do better, but people have a harder time applying them. And so I worry that this may happen in the future, but for right now, at least, we don't know where these failure cases might occur, but it's possible that they might exist.
Awesome, extensive answer. Thank you.
Hi, thank you for the great talk. I have just a very brief question concerning basically what you've done with this masking device. So you've always just said, okay, I'm going to mask 50% of the images, and half the time the cat image is in there, half the time it isn't. But I mean, in principle, you could do different stuff, right? You could just artificially construct 50-50 split-ups, putting in the cat image, putting not in the cat image, and then looking for smaller samples than 50%, looking for larger stuff, taking some images multiple times.
Yeah.
What are your insights concerning this? How does this influence the performance? And I mean, perhaps even this also connects to the diversity of the images, right? Sometimes 20% might suffice, sometimes not. So what are your insights on that?
Yeah, this is a good question. So yeah, we choose 50%. This is not sort of fundamental to the attack. In particular, we have some numbers where we sample with a different threshold. So we actually attack some real models where people train on the entire CIFAR-10 training data set. And here, what we do is we take the test set and we train partly on the test set, partly on the training set. And what this means is because of the ratio of these two data sets, we sample from the training data set with 5/6 probability each sample. And the attack works basically the same. You'll just get more values in the histogram corresponding to when it was in versus when it was out. The number here doesn't actually, I mean, 50% is just the best number to choose if you want to train as few models as possible. If you want to make sure that your models train on at least 80% of the data, you can do this. You just may need to train more models because you now have 20% of the models that don't, and so you still need at least like 5 models to compute a normal distribution, and so you'll need to train more models in general. But the number here is not hugely sensitive.
Thank you.
Hi, Mohammad Haroon from UC Davis. Amazing presentation. I was wondering if this attack could be adapted on the problem of attribute inference as well, where the possibilities for privacy concerns are much greater.
Yes, no, attribute inference, yes, we think this can be directly applied. In particular, there's a paper we've put out that doesn't do attribute inference by itself, but it does this sort of new clever attack of poisoning in order to improve various downstream attacks. And we show that we can use this attack to do, as a baseline, much, much better on attribute inference. And then if you're willing to do some additional assumptions, we can make it go even further. So one of the reasons we like this result is because it's general across not only membership inference, but attribute inference. And we show it can be helpful for data extraction and a couple other things. So we think it's a very general approach.
All right, thank you.
Yeah.
Right, maybe as a last question, to bring the session together with the usability and the attacks, what are like ideas to improve usability or issues, if there's anything you want to talk about?
To improve usability of what?
Of your presentation topic.
I see, to improve the usability of this attack, yeah. No, I think, yeah, the biggest thing right now is making it easier to, without having to train more models. This is, I think, the big thing that, if someone told me they couldn't apply this approach, probably the #1 reason I think it would be is because you have to train many more models. And I would like to be able to see approaches that don't require this. I'm a little skeptical here that this will be easy, just because fundamentally the way our approach works is by modeling things with Gaussians or distributions. And in order to make a prediction of a modeling, you need at least 2 samples, if not 4 or something. And so I think it's going to be interesting, but hopefully we can do better there, yeah.
Thank you. It doesn't seem like there are more questions. So thank you again, Nicholas, for your talk. Thanks everyone for this taking in.
Thank you.